Welcome to the Modern Analytics Academy vignettes. These are short, topical sessions that address new features and how to use them, frequent questions we receive, updates to previous sessions, or content that expand on topics previously covered. You will find the Modern Analytics Academy content as well as previous vignettes at aka.ms/MAA. In this Modern Analytics Academy vignette, we're going to focus on schema design in SQL Pools. In the original Academy sessions, 5 pillars of building a modern analytics solution were discussed. In this session, we're going to focus in on Pillar 2, modeling, and specifically within modeling, we're going to focus in on Azure Synapse SQL Pools. Here's an architectural diagram for a modern analytics solution in Azure. This was first introduced in the Modern Analytics Academy sessions. And what I want to focus on here is taking data from a variety of different data sources and different types and ingesting that data into your solution and storing that in your big data store. That will generally be Azure Data Lake Store. And then we can apply a variety of techniques and compute engines to work with that data. We might leverage Spark Pools in Azure Synapse or Azure Synapse SQL Serverless to explore that data, perform exploratory data analysis as an example. We might leverage Spark Pools or other machine learning techniques and compute engines to prep and train that data for machine learning workloads or in our analytical workloads. And then we might then take that data and present that data in a way that's available for reporting and analytics. And that's going to be the focus of our session today, is to talk about leveraging the Azure Synapse SQL Pools for data warehousing and preparing and serving that data for our end users. Azure Synapse SQL Pools is a dedicated relational data store leveraged within Azure Synapse Analytics. And since it's a dedicated relational data store, we're going to model our data much like we would a traditional data warehouse. A couple of things we want to consider as we think about an approach to modeling our data in our data warehouse is first a simplified access to data for reporting and analytics. We want to think about designing the schema in such a way that our business users can easily navigate the data model in order to perform queries and analysis with whatever tool that they may be using. The other item we want to consider is increasing performance. Since we're going to be leveraging a significantly large amount of data for doing our reporting and analytics, we want to ensure that the schema is designed in such a way that allows the database engine, in this case Azure Synapse Pools, to be most performant. Now, the method we're going to talk about here is dimensional modeling, which is a widely accepted modeling technique for building data warehouses and data marts. Dimensional modeling is centered around a business subject area or a business process. And what it allows us to do is to bring data together, and we're going to talk about these terms inside dimensional modeling here in just a moment. But this idea of conforming or bringing data and integrating data together is leveraging shared definition of various different data elements that can be leveraged across the business, across these business subject areas. And the other thing that we're going to consider is cleaning the data. And when we talk about cleaning the data, we're really talking about addressing missing items, different names of different fields or attributes that we want to unify in this conforming approach. So these are different things that we want to consider as we go into designing our schema for our Azure Synapse SQL Pools for reporting and analytics. I'd like to introduce the concept of dimensional modeling by comparing it to entity relationships or third normal form schema design. Now, entity relationships or third normal form schema design is used generally for transactional processing or OLTP, online transaction processing applications. These data models are normalized to provide efficiency for data inserts and updates or deletes within inside of a transactional application. One of their core design tenets is to reduce data redundancy, But in doing so, it's more efficient from an application perspective, but it's more complex for users, end users, or business users to understand the schema and to query the schema. So in contrast, dimensional modeling, which is a modeling technique generally used for analytical applications, used for data warehouse modeling, is a very good approach or technique for leveraging in self-service BI tools such as Power BI. And one of the design tenets here is to denormalize or to simplify the data model by supporting aggregations over large volumes of data. So again, the dimensional modeling is, and we'll get into these different models here in just a bit, is the idea of supporting end users, end user queries through a simplified schema design and allowing for increased performance in query. And to illustrate examples of these different schema techniques and design techniques, I'm going to be leveraging the Wide World Importer sample database. This is something that you could download from the Microsoft sample database website and deploy yourself. This represents the Worldwide Importer's transactional or OLTP, online transaction processing application. This is a small portion of the schema that represents orders or sales. As you can see, there's a variety of relationships, multiple relationships between the different tables to bring data together. Again, the idea is to reduce data redundancy, make it easy for single record inserts and updates from a transaction within inside of an application. And you can see the multiple tables that are broken out or normalized, if you will, into a third normal form between sales and invoices, customers, order lines, the details of the sales themselves, the sales order lines, as well as the people within the application. And in contrast to the schema that we just looked at, here's a dimensional model from the Worldwide Importer sample database from the data warehouse schema. And in this case, we see that a simpler schema design, fewer tables. And what we're going to see, and we'll get into more of these details, is these tables are denormalized where you're going to see redundancy in data. But the idea is we're introducing redundancy in data to simplify the schema so it's easier to navigate for business users or reporting tools in order to query. And it's more performant in the sense that there's less joins that we have to introduce for the query optimizer in order to return the large amount of rows that we're going to return. So again, this schema is designed for querying, returning large numbers of rows, and simplified user or navigation for user access. Now I'd like to get into the details of the components that make up a dimensional model. First, I'd like to talk about fact tables. Fact tables hold measures that we use for aggregations. Fact tables are often the largest table in the data model. Next, we have dimension tables. Dimension tables hold the descriptive attributes that we use for filtering and grouping of the measures in our fact table when we're doing reporting and analytics. Dimension tables describe entities within inside your data model. These could be customers, orders, as an example. And collectively, fact tables and dimension tables come together to create what we call a star schema. So going back to our Worldwide Importers dimensional model, here we see at the center of the diagram is the orders fact table. And here we see the surrounding tables are our dimension tables. We see employee, customer, stock item, date, and city. Collectively, these make up the star schema. So let's get into a little bit more about dimensions. Dimensions have a few different characteristics that we want to keep in mind as we're building our dimensional model and defining our schema. The first is surrogate keys. Surrogate keys are unique keys defined for the purpose of the dimensional model. These are essentially keys that we create in the schema and populate in the schema when we're doing our data load. The purpose of surrogate keys is to create relationships between the dimension tables and the fact tables in our dimensional model. Since we're not using business keys in order to do that, because we may not be able to guarantee uniqueness between the various different source systems in our business keys then become an attribute of the dimension table. A couple of other things that you may encounter as you're defining dimension tables in a star schema or dimensional model. One is role-playing dimensions. Now, role-playing dimensions is essentially a dimension table that we use for multiple purposes. A very common scenario would be date. We might have a single date table that we create in our dimensional model, and we might use that for the purpose of order date, shipping date, the sales date, and so on. So the idea is we're not actually recreating the physical table and restoring that data, but in our data model, we would leverage it through multiple relationships to perform that different role. The other piece that's important to understand that you may encounter is the idea of slowly changing dimensions. Now, data in a dimension table often changes much more slowly than the fact table. We'll talk more about the fact table in a moment, but the fact table is often increasing at a more rapid pace the ingestion of data. Information and attributes that we have about customers or products, as an example, are often going to change at a much slower pace. But there are techniques that we have to consider as we think about addressing these slowly changing dimensions, because it will have an impact on the way that data is queried and reported. And there are a variety of techniques to help us address the changes of data in our dimension tables. We're not going to get into those details today, but just want to highlight the fact that that is a consideration as you think about loading data and designing your dimension tables to addressing the slowly changing nature of data in these dimension tables. And we've been focused on this idea of a star schema. You saw some diagrams of the star schema where we have a single table connected directly to our fact table. There is another design technique that you may encounter that's referred to as a snowflake dimension. And a snowflake dimension is essentially an approach that's used to introduce some level of normalization to the dimension table. As an example, you might have, say, products at one of our sample databases leverages products where you would have a single table for product detail, another table that's joined to that with product subcategory, and then another table joined to that that's a product category. These three tables make up a normalized approach for a single entity referred to as product that's then broken down into subcategory and category. One thing to keep in mind is that additional work may be needed in analytical tools to consolidate these tables down for visualization or analytical views that you might leverage. And a few additional points about fact tables themselves. As I've mentioned already, they're measures, numerical values that we use to aggregate or summarize information from our business subject area. They're historical in nature and generally meaning that we continually add data. We don't change data in the past. We would add new data elements to the fact table. What we refer to as the level of granularity, or you may hear the term referred to as grain, is the level of detail that's stored in the fact table. One thing to keep in mind is that all the data that's stored in the same fact table should be at the same level or same level of granularity. So it could be at the day level, it could be at the month level. As an example, you might do summarization in various different techniques, but the granularity or the grain refers to the level of detail that's stored in the fact table, and it must be the same level of grain in order to ensure that we don't get double counting or other issues at the fact table. And then the keys inside the fact table map back to the dimension table, and that would be those surrogate keys. And as I mentioned already, increasing data volume for the fact table. Another type of fact table that you may or may not see is referred to as a factless fact table. And in this case, this is a fact table that does not contain any measures, just the keys only. And this is often used where you might be doing counting, where just the fact that a record exists inside of the dimension table is something that we can then aggregate via count over time, as an example. Returning to our worldwide importers dimensional model schema design or diagram here, just want to highlight a few things. One, going back to the fact table, here we see the keys. So again, these are the surrogate keys that are combined together to make up a unique key within inside of the fact table. And then these would be joined back to the dimension tables. So in this case, we see we've got the customer key and the customer dimension and the corresponding key in the fact table. So these two keys are used to create the join between our dimension table and customer and the fact table for orders. And as I mentioned previously, in the customer dimension, we see the customer ID, which is now being used as an attribute. So this is the business key that we're using as an attribute within the customer dimension and not as the key to join to the fact table. And here we see an expanded view of the fact table, and I just wanted to highlight where we saw previously the keys, the surrogate keys that make up the composite key for the fact table that connect our dimension tables. These additional fields are our actual measures that we would use for aggregation. It could be for count, where we see order ID or back order ID, or other types of measures that we would have for various different aggregations that we would do in our reporting and analytics. And one area I wanted to just highlight as we see the various different dimensions that we have around our fact table, our order fact table, stock item, customer, employee, city in this case. I did want to highlight the notion of the date dimension. Very common that you would always have a date dimension. This might be something that you create through your ETL or extract, transformation, and load process. But very common you would have a date dimension that you would leverage in your reporting and analysis. And here we see an expanded view of the date dimension just to highlight some of the potential attributes that you may find. There may be other attributes depending on your business, if there's seasonality or other types of factors that you want to do analysis on. But here we see month, calendar year. You see the month itself, then you see calendar month number, calendar month label, which would be the name itself. The calendar month number is something that you might use for, depending on the reporting tool, for sorting calendars. So you're sorting in the non-alphabetic order as an example. So these are just some attributes that you might find in the date dimension. As I mentioned previously, the date dimension is something that you would almost always see in a dimensional model and something that provides a lot of value for reporting and analysis over time. So as we conclude our session today, I wanted to return to the architecture diagram for a modern analytics solution in Azure. We talked about taking data from a variety of different data sources and a variety of different data formats and ingesting that data and storing that in Azure Data Lake storage. From there, we can apply a variety of different compute engines and techniques depending on what our specific needs and requirements are to that data to serve that to our business users, our data scientists or analytic users, and so on. Our focus today was on the data warehouse, specifically Azure SQL Pools, the dedicated pools, which is a relational data engine for serving up data. And we talked about the modeling capabilities and approaches that we would take in preparing that data, modeling that data to make it easy and performant for our business users to consume that data in a variety of tools. This is also a technique that can be applied directly in Power BI. Similar concepts apply. And you might use Power BI to directly connect to and query the Azure SQL Pools as a data warehouse in order to report and perform analysis on that data. Now we've really just touched the surface on the concepts of dimensional modeling. This was a short introduction to the idea of the importance and the reasons why we would do dimensional modeling for our Azure Synapse SQL Pools as a dedicated relational serving layer inside of Azure Synapse Analytics. I wanted to leave some additional resources if you have an interest to go deeper in this topic. The first is an article that talks about the importance, well, one, understanding star schema design and the importance for Power BI. As I mentioned earlier, these techniques can be applied to Power BI. This article is very relevant as well as it relates to the concepts from a deeper perspective for Azure Synapse SQL Pools. And we also have a Microsoft Learn module on designing a multi-dimensional schema to optimize analytical workloads. Again, concepts apply to what we're doing here with Azure Synapse SQL Pools, so a very valuable learning resource there as well. And there's a tremendous amount of information that you can research and learn about dimensional modeling, the different techniques to handle different scenarios. And I wanted to call out this particular book. This is a great reference and resource, the Data Warehouse Toolkit, The Definitive Guide to Dimensional Modeling by Ralph Kimball. Great resource to understand not only the introductory concepts of dimensional modeling, but also in-depth modeling techniques to address and handle a variety of different scenarios that you'll experience in modeling various different business subject areas. And as we continue to deliver additional vignettes in the future, I would encourage you to take a look or keep an eye out for the Synapse Data Explorer vignette, future session on Synapse database templates, which are templates that are built into Azure Synapse Analytics for doing very much the same type of activity that we discussed today, but for Azure Synapse SQL serverless. We'll also talk about taking the concept that we described today and talk about Synapse partitioning and the approach of doing partitioning in the Azure SQL Pools, as well as Dataverse and how modeling from the Dataverse applies to Azure Synapse Analytics. And finally, thank you very much for your time today. I appreciate the time and attention for attending our session and look forward to future vignettes. Thank you.